look at a second example now. This is the function f of x equal to sine x over the domain from 0 to pi. Okay, so first we recognize that the period is pi and the frequency nu0 is 1 on pi. Looking at the function, also we can see that the average is not 0, so there will be an offset in our Fourier series. And also, the Fourier series is going to be even, because if we take this pattern here and imagine printing it to the left and to the right, repeating it periodically in this domain, we'll end up with something which is even about the origin here. That means the odd terms, the b terms, the sine terms, will be 0. Just to prove that, we can compute this integral for the b terms, which is given by this. So we're integrating over the interval 0 to pi, the function f of x, which is sine x, multiplied by the sine terms. We can expand this product of sine functions into a difference in cosine terms and integrate, and we get 0, because the sine of all these odd things here is going to be 0 at 0 and pi. Okay, that's the uninteresting b terms. What about the interesting a terms? Well, as I foreshadowed, there will be an offset. We find that a0 is 4 divided by pi, and am is given by this integral here, and we can compute that, again expanding a product of harmonics into a difference or sum of harmonics, and I won't go through the details of that, but you get am is equal to this quotient here. Which leads us to our Fourier series, which is 2 divided by pi minus this sum here. Great, so we've got an infinite sum. Let's see how well it converges to our function. So what I've plotted here is the 0th term, which is the offset of this function, which is 2 on pi, and I've added in the first sine term already, sorry, the first cosine term already. And now let's keep adding the terms, and you can see it converges really fast. So we'll just go back and slow that down. That's the n equal to 1 term, n equal to 2, 3, 4, 5. Already by the time we get to n equal to 20, it's very close to the blue curve. And by the time we get to 100, it's almost indistinguishable. If we look at the spectrum of the terms, then we can see, this is reflected in that behavior is reflected in the spectrum, in that the first few terms are fairly large, but then the amplitude of the terms is close to 0 after not very many terms. So as we add each successive term, it has less and less of an effect, because we're approximating this function very quickly with quite few terms. There's no Gibbs phenomenon here either, because there's no discontinuity. There's a undefined derivative at this point, but there's no step discontinuity.